If you want an AI to write a poem or like summarize a document, you can just scrape the entire internet for text.
Right. You have billions of examples ready to go.
Exactly. You have all this human thought ready to be tokenized.
Okay.
But if you want $1 million robotic arm to learn how to chop an onion or fold a shirt, you have a massive problem.
Yeah, a very expensive problem.
Because if the robot guesses wrong during training, it doesn't just output a weird string of characters. It physically smashes a knife through a table or, destroys its own motors.
Right.
So, welcome to AI Paper Swap, the YouTube series where we get straight into the signal and cut out the noise. If you're building, researching, or just trying to stay current in machine learning, you're in the right place. Today, we are doing a deep dive into a really massive position paper called Robots Need More Than VLAs and World Models.
And it's by a really heavy-hitting consortium, right?
Yeah. Researchers from Motoni.ai, Stanford, ETH, Zurich, IIT, TU Darmstadt, and UCL. So here's your 60-second core insight. The entire robotics field right now is completely obsessed with scaling vision language action models.
The VLAs.
Right. And the prevailing thought is basically if we just feed these models more robot demonstration data, we get better generalist robots.
Which makes sense on paper.
It does. But this paper argues that this whole policy scaling framing is fundamentally incomplete. It's actively hitting a bottleneck. We don't just need larger models, we actually need a 4-pillar architectural stack that can ingest the world's abundant, messy, unstructured behavioral data.
Like internet videos and human motion capture.
Exactly. Random tactile sensor streams, all of it.
Yeah.
And the stack needs to actually auto-label it into grounded, robot-usable supervision. The goal is extracting actionable contacts, object states, and task condition rewards automatically.
It's honestly a fundamental shift in how the field views the whole data pipeline.
Yeah.
Because we're looking at a transition away from a paradigm that's strictly bottlenecked by explicit robot demonstrations. We're moving toward one that basically attempts to turn the entire physical world into a training environment.
Right.
But to understand why that transition is so difficult in the first place, we really need to look at how we currently train these systems.
Okay, let's unpack this. I think the best way to visualize the current paradigm and why it's hitting a wall is to think about learning to cook.
Oh, I like this analogy.
Right, so training robots today is essentially like trying to learn to cook a complex meal. But you are only allowed to learn if a master chef physically stands behind you.
Wow, okay.
Yeah, like they grab your arms and physically guide your hands for every single chop, stir, and pinch of salt. You aren't allowed to just watch a YouTube cooking tutorial and figure it out.
You can't just infer it.
Exactly. You need that physical one-to-one mapping.
That master chef analogy perfectly describes what the authors call the robot native regime.
Robot native regime, okay.
Yeah, and we have to acknowledge that this direct, hand-guided approach has driven some undeniable progress recently. I mean, the field has seen a huge push to pool multi-robot data sets to feed this regime.
Right, like Droid, I think.
Exactly. Droid has something like 76,000 demonstration trajectories collected across hundreds of scenes. And then we have Bridge Data V2.
Oh, and the OpenX Embodiment project, right?
Yes, the massive one, pooling over 1 million trajectories from 22 different robot embodiments.
It's a huge amount of data.
Yeah.
And that data is fueling the vision language action models that are making all the headlines right now.
The ones everyone is talking about.
Yeah, we're talking about architectures like RT1, RT2, OpenVLA, Figures Helix, and NVIDIA's GR0T for humanoids.
Yeah.
And they seem to be working exceptionally well.
They do.
So I think a lot of engineers might wonder why this paper claims the paradigm is broken.
Well, those models work well precisely because the data they're trained on is already perfectly expressed in the coordinate system of the robot.
What do you mean by that?
So you have proprioceptive states, meaning the robot knows the exact position of its own joints paired with camera feeds. And crucially, exact motor commands and explicit task labels.
Oh, so the action space is native to the hardware.
Exactly. A neural network can easily optimize for that objective because the heavy lifting is already done.
The translation work.
Right. The translation work of figuring out how to move the arm to achieve the goal has already been done by the human who was teleoperating the robot during the data collection.
So the human operator acted as the computational bridge there.
Completely.
But the catch, and I guess the crux of the problem the authors point out, is that robot native data is insanely expensive to acquire.
Oh, unbelievably expensive.
I mean, scraping Wikipedia for an LLM costs fractions of a cent per megabyte. But every single trajectory in that OpenX embodiment dataset had to be physically executed in the real world.
By a person.
Yeah, a human had to put on a VR headset or use a joystick, guide the robot, reset the physical environment, and just do it again.
And furthermore, every action recorded is tied to one specific body type.
Right.
Like a trajectory recorded on a universal robot's arm doesn't perfectly map to a Franca arm.
Because the joints are different.
Exactly. So the robotics field has finally had its foundation model moment, but it lacks its internet.
That's a great way to put it. We have millions of hours of humans cooking, cleaning, and building on YouTube.
Right.
But that video completely lacks embodiment-specific action labels and, like, force signals.
And the field has certainly tried to bypass this bottleneck, you know?
Yeah, of course.
The obvious response to the expensive robot-native data is to try and find a way to learn from that vast ocean of passive internet video.
Or generate it, right?
Yeah, alternatively, researchers look to generate infinite cheap data in physics simulators. But the paper outlines why those bypasses are currently falling short.
Well, let me push back on the author's premise here on behalf of the listener.
Yeah.
Because researchers are actively using passive video right now.
They are, yeah.
We have representation learners like R3M and VIP that are pre-trained on huge data sets of human video, like Ego 4D.
Mm-hmm.
And we have latent action approaches, too. Models that watch a video and extract a mathematical representation like a transition code of what just happened. I think LAPA does this.
Yeah, LAPA is a
Yeah.
good example.
Right. So if a model watches a human open a drawer and extracts a latent action code for that movement, isn't that essentially a robot action? Why isn't that enough to bridge the gap?
What's fascinating here is that this gets to the absolute heart of what the paper calls the embodiment gap.
Okay.
A latent visual code extracted from a video is not a robot command, period.
It's not.
No. When an AI watches a sequence of video frames showing a human opening a drawer, it receives an observation sequence.
Right, the pixels.
Exactly. It sees the pixels change from frame 1 to frame 2 to frame 3, but it completely lacks the robot action sequence.
Ah, I see.
The latent variable might perfectly explain the visual transition. It captures the semantic concept of drawer opening.
But it doesn't know how to physically do it.
Right. If you pass that visual concept to a robotic arm with parallel jaw grippers, the hardware controllers have absolutely no idea what motor torques to actually apply to the joints.
Wow. Okay, I see the distinction. The AI understands the semantic meaning of the action. It knows a drawer opened, but it lacks the inverse kinematics.
Exactly.
It just doesn't know the physical force required to make those pixels change.
Precisely. Observing physical change is fundamentally different from executing a kinematic and dynamic action.
Yeah.
The video tells you what happened, but it totally strips away the invisible forces, the friction, the weight of the drawer.
And the specific muscle movements that made it happen.
Yep.
Okay, so passive video fails because it lacks physics and motor commands. What about the simulation route then?
Simulation is interesting.
Because we have highly advanced environments like RL Bench, MetaWorld, and Manaskill. And more recently, we're seeing incredible generative world models. Like DeepMind has Genie, right?
Yes, GA.
And there are sim-to-real bridges using 3D Gaussian splatting, like RLGS Bridge. So if we can't extract actions from YouTube, why can't we just generate the required action label data inside a hyper-realistic simulated world?
Well, we can try. But the authors emphasize that robotics places far stricter demands on world models than standard video generation does.
How so?
A model like OpenAI's Sora or Google's Lumiere might generate visually stunning, hyper-realistic videos of a scene, but visual plausibility is not the same thing as physical grounding.
Oh, I think I see where the danger lies here.
Yeah.
If a standard AI video generator hallucinates an extra finger on a human hand or, like, makes a shadow face the wrong way, it looks weird, but it's harmless.
It's just a funny artifact on Twitter.
Right. But if a robot's internal world model hallucinates that a glass cup can simply pass through a solid wooden table because the neural network didn't strictly enforce collision physics,
Then you have a real problem.
the robot will literally smash the glass into the table in the real world. The cost of a physics hallucination in robotics is hardware destruction.
And that is a cost researchers simply cannot afford to pay.
Right.
A useful robot world model must preserve the variables that actually dictate physical reality,
Like what?
like 3D geometry, object permanence, material properties, friction, and exact contact points.
That's a lot to simulate accurately.
It is. And to prevent these destructive hallucinations, the paper points to the absolute necessity of calibrated uncertainty estimates.
Okay.
They reference work by May and Ward, highlighting that a world model basically needs to know when it doesn't know.
Interesting.
If the model is uncertain about a dynamic prediction, say, how a bizarrely shaped object will tumble if pushed, it needs to flag that uncertainty.
Rather than just confidently generating a physically impossible hallucinated outcome.
Exactly.
So how do they actually solve that computationally? I mean, how do you force a neural network to respect physics?
Well, the authors point to the need to combine neural scene representations with actual hard-coded physical simulation engines.
Oh, combining them.
Yeah, a great example they cite is Contact Gaussian WM. It integrates 3D Gaussian splatting, which handles the visual rendering, with actual differentiable contact dynamics.
So it's doing two things at once.
Right, so the model isn't just predicting what the next pixel should look like based on patterns in its training data. It's running a parallel calculation that strictly enforces the preservation of physical variables like mass and friction during collisions.
Okay, so to summarize the wall we're hitting here,
Yeah.
pure robot data is too expensive to scale.
Right.
Passive human video lacks motor commands. And standard generative simulators hallucinate physics that destroy hardware.
That's the trifecta of problems.
Which leads us into the paper's actual solution.
Yeah.
They propose a new physical intelligence pipeline built on 4 pillars.
Yes, the 4 pillars. Pillar 1 is what they call physical data engines and embodied autolabeling.
Okay.
This engine is designed to take in incredibly messy, heterogeneous, asynchronous data streams.
What kind of data?
We're talking about raw video, data from wearable motion capture suits, tactile sensors, raw robot logs, and language instructions.
That is messy.
Extremely. And the engine's job is to align all of this raw data into a structured, latent event timeline.
I want to make sure we understand the mechanics of this. What does that actually look like in practice? How does it transform the data?
Okay, imagine a human wearing a sensor-rich suit demonstrating how to place a heavy ceramic cup on a metal tray.
Okay, got the visual.
The physical data engine doesn't just record a continuous video, it processes the visual data alongside the force feedback from the suit.
Oh, so it feels it too.
Exactly. And it segments that continuous action into discrete physical events.
Like what?
Event 1, the arm reaches for the cup. Event 2, contact begins between the fingers and the ceramic. Event 3, the fingers exert enough force to establish a stable grasp.
And event 4 would be lifting it, maybe?
Right. Event 4, the object is lifted and the weight shifts. In this paradigm, wearable sensing suits aren't just being used for direct teleoperation.
Oh, wow.
They are highly sophisticated labeling instruments. They automatically provide the ground truth physical labels.
The exact force vectors.
Yes, the force vectors, the exact millisecond contact was made, the distribution of weight, things that an ordinary YouTube video completely hides.
Here's where it gets really interesting, though. Because even with that perfect auto-labeled data, we still have a hardware mismatch.
Always.
Let's say we use Pillar 1 to perfectly capture a human's hand grasping that ceramic cup. The system logs the exact angle of all 5 fingers and the force applied. Making a robot perfectly mimic the exact 3D pose of those 5 human fingers is completely useless if the robot only has a 2-pronged parallel jaw gripper, or like a suction cup.
Right. The human's specific joint angles are entirely irrelevant to the robot.
Exactly.
And that is why Pillar 2 is task-preserving retargeting. This pillar directly addresses the embodiment gap we discussed earlier.
Right, because the goal isn't matching the pose, it's matching the effect on the world. The cup needs to be secured and lifted.
Yes.
The robot needs to translate the intent of the human's 5 fleshy fingers into instructions for its 2 metal prongs. So how does Pillar 2 compute that translation?
The authors break down a hierarchy of retargeting to achieve this mapping.
A hierarchy, okay.
Yeah. At the lowest, weakest level, you have pose preservation. That's just trying to blindly copy the arm trajectory, which, as we establish, fails if the bodies are different.
Right. It doesn't work.
Above that, you have contact preservation. The system calculates how to ensure the robot's specific end effector touches the same relevant surfaces of the object at the same moments the human did.
Okay, that's better.
Higher still is object state transition preservation. Now the focus shifts entirely to the object.
So ensuring the drawer actually opens or the cup is actually lifted.
Exactly, regardless of the kinematics used to achieve it.
And the highest level of that hierarchy.
Preserving intent or skill.
Uh-huh.
The robot might use a completely different set of motions or a different approach angle than the human, but it accomplishes the exact same task under the same physical constraints.
That makes sense.
And the critical detail here is that this high-level retargeting is only computationally possible because the physical data engine from Pillar 1 is feeding the system those exact auto-labeled physical changes.
Because Pillar 1 isolated the contact events and force requirements.
Right. So Pillar 2 has the mathematical targets it needs to optimize the robot's specific motors.
It's a brilliant handoff. The data engine isolates the physics of the human demonstration, and the retargeting layer maps those physics to the robot's hardware.
Seamlessly.
But, okay, if the robot now knows how to translate my human grip into its metal claw grip, what stops it from confidently miscalculating the weight of the cup and crushing it?
Good question.
I mean, it has a plan, but how does it test that plan safely?
That is where Pillar 3 comes in. Physics-grounded world models for consequence prediction.
Consequence prediction.
Yeah. Once the retargeting layer generates a potential action plan, the robot uses the world model as a counterfactual reasoning engine.
Meaning it plays out the what-ifs.
Exactly. It mentally simulates the action before taking it. It asks, if I apply this specific torque to my parallel jaw gripper, what physically changes in the world and why?
And to tie it back to what we discussed earlier, this is where that integration of differentiable contact dynamics becomes vital.
Yep.
The robot isn't just generating a visual prediction of the cup, it's running a physics simulation of the forces.
Yes. And crucially, the authors emphasize that this consequence prediction must be task conditioned. However, if the task is sliding a heavy wooden block across different surfaces, friction and mass become the critical variables to predict, and deformable geometry becomes completely irrelevant.
So the system models what matters.
It models what matters.
I like that. But that leads us to a fundamental question about how an AI evaluates its own success, which brings us to Pillar 4, task-conditioned reward grounding.
This is a big one.
Let me put you, the listener, in the perspective of the robot for a second. Imagine you're a robot looking through your camera at a visual state where a glass cup is sitting perfectly still on a kitchen table.
Okay.
How do you know if that state is a good state or a bad state? Did you succeed or fail?
Well, a standard ungrounded visual model might analyze the image, recognize that the cup is upright and not broken, and determine that it's a positive, stable state.
But the true answer is that the state itself is completely neutral until it's grounded in the context of the task.
Exactly.
If the original command was pick up the cup, then the visual state of the cup sitting on the table is a complete failure. You missed.
You didn't do the job.
But if the goal was put the cup down safely, then that exact same visual state, the identical arrangement of pixels, is a massive success.
Task-conditioned reward grounding provides the system with the logic to evaluate its own actions based on the initial intent.
It gives it context.
Yes. And if we connect this to the bigger picture, this evaluation engine powers the final, most crucial piece of the author's vision,
Which is?
this self-improving deployment loop. This is where all 4 pillars come together to solve the data bottleneck we started with.
If this self-improving loop actually works, it sounds like every single time a robot makes a mistake in the real world, it generates training data for the whole fleet. Is that the end goal here?
That is exactly the goal.
How does the loop actually function mechanically, though?
Well, we have to completely change how we view robot deployments. Right now, deployments are often treated as simple pass or fail tests.
Right.
In the paradigm this paper proposes, every single real-world robot rollout, especially the failures, is captured and processed as a fully labeled physical episode.
So if a robot in a warehouse tries to grasp a slick, heavy package and drops it, that isn't just an error log. That failure is actually valuable data.
It's arguably the most valuable data. The dropped package triggers the entire loop.
Walk me through it.
First, the physical data engine from Pillar 1 automatically analyzes the sensor logs and auto labels the exact moment the failure occurred.
So it detects a slip caused by insufficient force, maybe.
Exactly. Then the task-conditioned reward grounding from Pillar 4 registers this as a failure state for the specific task of lifting.
Okay.
This feedback is then sent to the physics-grounded world model in Pillar 3, which realizes its previous prediction about the package's friction was wrong, and it updates its internal friction parameters.
Oh, wow.
Finally, the policy and retargeting layer in Pillar 2 calculates a new, firmer grip for the next attempt.
It creates a closed-loop system that compounds in intelligence with every single physical interaction.
It learns on the job.
It's no longer reliant on a human teleoperator having to physically demonstrate the firmer grip. The system recognized the failure, modeled the physics of why it failed, and adjusted its own parameters.
It's a massive paradigm shift. It offers a roadmap for moving from a regime where we hand-feed robots expensive curated data to a regime where robots can actually ingest, analyze, and learn from the messy, chaotic, physical reality we live in.
So to synthesize this whole architecture for everyone listening, the authors of this paper are making a bold claim about the future of the industry.
They really are.
The next true foundation model in robotics is not going to be a monolithic, multi-billion parameter VLA model that just ingested more YouTube videos.
No, you can't just brute force it.
Right. You cannot simply scale your way out of the embodiment gap with more compute and more ungrounded pixels. The future is a compounding system.
Built on those 4 pillars.
Exactly. It requires a physical data engine for auto-labeling messy inputs, an embodiment retargeting interface to translate human intent to specific robot hardware, a physics-grounded counterfactual model to safely predict the consequences of an action, and a self-improving deployment loop to turn every real-world failure into high-quality supervision.
And look, the transition will require incredibly complex engineering, particularly in integrating those differentiable physics engines with neural representations.
It's not going to be easy.
Not at all. But the theoretical framework they present is a compelling answer to the current data bottleneck.
It really is.
Yeah.
I want to leave you, the listener, with a final provocative thought to mull over based on this research.
Let's hear it.
We spent a lot of time today talking about using human motion capture and wearable sensing suit to teach robots how to manipulate objects. We want to teach them how to grasp a cup, how to open a drawer, how to slide a block.
At physical mechanics.
Right. But there is a secondary, perhaps even more profound implication hiding in this approach to data collection.
What's that?
All of this human behavioral data isn't just teaching the robot about the objects in the environment. It's actually serving to build a collaborative, natural working model of human behavior itself.
Oh, that's an interesting point.
Yeah, as we move toward a future where generalist robots are operating in our homes, our kitchens, and our factory floors, the ultimate challenge might not actually be learning to manipulate the physical world.
What will it be?
The ultimate challenge might be learning to seamlessly, predictably, and safely collaborate with the humans living inside it. Understanding our intent from our physical motion, knowing why a human reaches for a cup in a certain way, might be the key to building robots that don't just work for us, but are capable of truly working with us.
That's powerful.
Understanding the physics of the world is only half the battle. Understanding the physical intent of the human operator might be the other.
I agree completely.
Well, that is all the time we have for today's deep dive. Thank you for joining us on AI PaperSwap.
It was a great discussion.
We highly recommend you track down the full paper, Robots Need More Than VLAs and World Models, and keep exploring the research on your own. Remember, we are trying to move away from the master chef holding our hands. We have to build the systems that let the robots watch, understand, and learn the physics of the world for themselves. Catch you next time.